So here's something to think about as you settle in tonight. Right now, somewhere on this planet, there are about 440 nuclear reactors running, quietly, constantly, splitting atoms, boiling water, pushing electricity out across thousands of miles of power lines into homes and hospitals and streetlights. And the whole process, the fundamental thing happening inside those reactors, involves a reaction so powerful that a single kilogram of uranium fuel contains roughly the same amount of energy as 2,700 tons of coal. That's not a typo. 1 kilogram versus 2,700 tons. The energy density of nuclear fuel is almost incomprehensibly vast, and the story of how human beings figured out how to tap into it is one of the most dramatic, consequential, and morally complicated stories in the entire history of engineering. And that's what we're going to talk about tonight. Nuclear power. The whole thing, from the very beginning, from the first accidental discoveries that nobody understood, through the secret wartime laboratories, through the gleaming promises of atoms for peace, through the catastrophic accidents that shook entire nations, all the way to the debates happening right now about whether nuclear energy might be the thing that saves us from climate change, or whether it's simply too dangerous to trust. We're going to take our time with it. There's no rush. If you drift off somewhere along the way, that's absolutely fine. The story will still be here. And honestly, there's something fitting about falling asleep to a story about the most concentrated form of energy human beings have ever harnessed. Let that power hum quietly in the background while you rest. Let's start where the story actually starts, which is the very end of the 19th century. And the discovery that kicked the whole thing off was, like so many great discoveries, a complete accident. The year is 1896. The place is Paris, and the man at the center of it is Henri Becquerel, a French physicist from a family of physicists. His father and grandfather had both been prominent scientists, and Henri had inherited their laboratory at the Muséum National d'Histoire Naturelle. He was studying phosphorescence, which is that phenomenon where certain materials absorb light and then glow for a while afterward. Think of those little glow-in-the-dark stars you might have had on your bedroom ceiling as a kid. You charge them up with a lamp and they emit a soft green glow in the dark. That's phosphorescence. Now, Becquerel was specifically interested in whether phosphorescent materials might emit X-rays. X-rays had just been discovered the year before, in 1895, by Wilhelm Röntgen in Germany, and that discovery had caused a sensation. Röntgen had found that certain rays, invisible to the eye, could pass through solid objects and expose photographic plates. He took that famous ghostly image of his wife's hand, showing her bones and her wedding ring, and the world went wild. Within months, doctors were using X-rays to see inside bodies, and physicists everywhere were scrambling to understand where these mysterious rays came from. Becquerel wondered whether the glow from phosphorescent minerals might include X-rays, so he set up an experiment. He took some uranium salts, potassium uranyl sulfate, specifically, a yellowish crystalline compound, wrapped a photographic plate in black paper to keep out visible light, placed the uranium salt on top, and put the whole thing in sunlight to activate the phosphorescence. When he developed the plate, there was a silhouette of the uranium salt, exactly as if X-rays had passed through the black paper and exposed the film. So far, so expected. The phosphorescent material was glowing, and part of that glow seemed to include rays that could penetrate paper and fog a photographic plate. But then something happened that changed everything. Paris went cloudy. For several days, there wasn't enough sunshine to activate the phosphorescence, so Becquerel put his experimental setup away in a desk drawer. The wrapped photographic plate with the uranium salt sitting on top of it, unexposed to sunlight. He left it there, and a few days later, maybe just for completeness, maybe out of idle curiosity, he decided to develop that plate anyway, expecting to see at most a very faint image, since the uranium hadn't been energized by the sun. The image wasn't faint. It was strong, clear, vivid. The uranium salt had been sitting in a dark drawer, with no sunlight to activate any phosphorescence, and yet it had still produced intense rays that penetrated the black paper and exposed the photographic plate. This had nothing to do with phosphorescence. The uranium was emitting these rays all by itself, continuously, without any external energy source. Something was coming out of the uranium, some kind of invisible radiation, and it wasn't stopping. Think about what that means. In 1896, the prevailing understanding of physics said that energy doesn't just appear from nowhere. Conservation of energy, one of the most fundamental laws of thermodynamics, says you can't get energy output without energy input. And yet here was a chunk of uranium, sitting in a dark drawer, quietly radiating energy with no apparent source. Where was the energy coming from? Becquerel didn't know. Nobody knew. But the discovery that certain elements spontaneously emit radiation, what Marie Curie would soon name radioactivity, was about to open a door onto an entirely new layer of physical reality, one that would take decades to understand, and would ultimately unleash powers that would reshape civilization. And speaking of Marie Curie, she's the next essential character in this story, and honestly, one of the most remarkable human beings who ever lived. Born Maria Sklodowska in Warsaw, Poland in 1867, she grew up under Russian occupation, in a family that valued education fiercely, but had very little money. Her mother died of tuberculosis when Marie was 10. Her father was a physics teacher whose career was hampered by the Russian authorities. As a young woman, Marie couldn't attend university in Poland. The University of Warsaw didn't admit women, so she worked as a governess and a tutor for years, saving money, while also attending illegal underground classes organized by Polish intellectuals. In 1891, at the age of 24, she finally scraped together enough money to move to Paris and enroll at the Sorbonne. She lived in a tiny attic apartment, sometimes too poor to heat it or to buy food. She reportedly fainted from hunger during lectures, but she earned 2 degrees, in physics and mathematics, graduating at the top of her class. She married Pierre Curie, a French physicist, in 1895. Their courtship was itself a kind of physics experiment. Marie was initially reluctant, focused entirely on her studies, and Pierre wooed her, partly by talking about magnetism and crystal symmetry, which is either deeply romantic or deeply nerdy, depending on your perspective. Pierre was a brilliant scientist in his own right. He and his brother Jacques had already discovered the piezoelectric effect, the phenomenon that makes quartz crystals produce a tiny electric current when squeezed, and conversely, vibrate at a precise frequency when an electric current is applied. That property is the technology inside every quartz watch and every digital clock. Together, Marie and Pierre formed one of the most productive scientific partnerships in history. When Marie was looking for a subject for her doctoral research, she chose Becquerel's mysterious rays. It was a bold choice. Most senior physicists considered the topic a curiosity, a sideshow to the main drama of physics. Marie saw it differently. She sensed that these rays were pointing toward something fundamental, something that nobody had yet grasped, and her approach was characteristically thorough and systematic. And when Marie was looking for a subject for her doctoral research, she chose Becquerel's rays. She wanted to understand this strange, spontaneous radiation that uranium emitted, and her approach was methodical, rigorous, and ultimately revolutionary. Marie developed a technique using an instrument Pierre had helped design, a sensitive electrometer that could measure extremely small electric currents. Radiation ionizes the air around it, stripping electrons from air molecules. And ionized air can carry a tiny electric current. By measuring that current precisely, Marie could quantify the intensity of radiation from different materials, and she made two crucial discoveries. First, she found that the intensity of radiation from a uranium sample depended only on the amount of uranium present, not on its chemical form, not on temperature, not on whether it was solid or dissolved in acid. This told her that the radiation wasn't a chemical phenomenon. It was something coming from the uranium atoms themselves. She was seeing something atomic, something fundamental. Second, and this was the discovery that really set things in motion, she found that certain uranium ores, particularly a mineral called pitchblende, were significantly more radioactive than pure uranium. That shouldn't have been possible. If uranium was the source of the radiation, then pure uranium should be the most radioactive thing around. The fact that pitchblende was more radioactive meant that it must contain something else, something even more radioactive than uranium, something nobody had discovered yet. Marie was sure of it, and she set out to find it. What followed was one of the most grueling laboratory efforts in the history of science. Marie and Pierre, working together in a converted shed that had previously been used as a dissection room, leaky roof, dirt floor, no proper ventilation, spent years processing tons, literally tons, of pitchblende ore. They were doing industrial-scale chemistry in a space that a modern safety inspector would have shut down in seconds. Marie would stir massive boiling vats of ore, dissolved in acid, then perform careful chemical separations to isolate the unknown radioactive elements. It was back-breaking physical labor combined with exquisitely precise analytical chemistry, and in 1898, they announced not one but two new elements. The first they named polonium, after Marie's homeland of Poland, which was still under Russian control. The second they named radium. And radium turned out to be extraordinarily radioactive. Roughly 1,000,000 times more radioactive than uranium, gram for gram. When Marie finally isolated a tiny speck of pure radium chloride, it glowed in the dark with an eerie blue light. She kept a vial of it on her bedside table, marveling at how it shimmered in the night. She didn't know it was killing her. Here's the thing about the early days of radioactivity research. Nobody understood what radiation actually did to living tissue. Nobody knew about DNA damage, about cellular mutations, about the cascade of biological destruction that ionizing radiation causes at the molecular level. Pierre Curie actually strapped a vial of radium to his arm for 10 hours to see what would happen, and reported that it produced a burn that took weeks to heal. They noticed that they were frequently tired, that they had sores on their hands, that Pierre had chronic bone pain. They attributed it to overwork. Marie Curie would carry test tubes of radioactive material in her coat pockets. Her personal effects, her notebooks, her cookbook, even her furniture, are still so radioactive that they're kept in lead-lined boxes at the Bibliothèque Nationale de France, and researchers who want to consult them have to wear protective clothing and sign liability waivers. This will be true for another 1,500 years or so, until the contamination decays to safe levels. Marie Curie became the first woman to win a Nobel Prize, sharing the 1903 Physics Prize with Pierre and Becquerel. Then, after Pierre was tragically killed in 1906, he stepped into a Paris street, distracted, and was struck by a horse-drawn wagon. Marie continued their work alone, eventually winning a second Nobel Prize, this time in chemistry, in 1911, for her discovery of radium and polonium. She remains the only person ever to win Nobel Prizes in 2 different sciences. She died in 1934 of aplastic anemia, almost certainly caused by decades of radiation exposure. She was 66 years old, and the science she pioneered, the understanding that atoms themselves contain enormous hidden energy, was about to take the world in directions she could never have anticipated. Because here's what nobody yet understood at the turn of the 20th century. They knew that certain atoms spontaneously emit radiation. They knew this radiation carries energy, but they didn't know where the energy was coming from, and they didn't know the structure of the atom itself. Remember, in 1900, there was still serious debate about whether atoms even existed as physical objects, or were just useful mathematical fictions. The discoveries that would reveal the true structure of the atom, and the staggering amounts of energy locked inside its nucleus, were still coming, and they would come fast. Ernest Rutherford is the person who cracked the atom open, figuratively and eventually literally. Born in New Zealand in 1871, the son of a flax farmer, Rutherford won a scholarship to Cambridge, where he worked with J.J. Thomson, the man who discovered the electron. Rutherford was big, loud, energetic, and possessed of a powerful experimental intuition. He moved to McGill University in Montreal, then to the University of Manchester, and everywhere he went, he produced groundbreaking work on radioactivity. He identified 2 of the 3 types of radiation emitted by radioactive materials: alpha particles, which turned out to be helium nuclei, and beta particles, which turned out to be high-speed electrons. He won the Nobel Prize in Chemistry in 1908 for his work on radioactive transformations, and famously joked that of all the transformations he'd studied, none was quite as rapid as his own transformation from physicist to chemist. But the discovery that matters most for our story came in 1911, when Rutherford and his colleagues Hans Geiger and Ernest Marsden performed that famous gold foil experiment. They fired alpha particles at a thin sheet of gold and found that while most went straight through, a tiny fraction bounced almost straight back. This led Rutherford to propose the nuclear model of the atom, a tiny, incredibly dense, positively charged nucleus at the center, surrounded by orbiting electrons in mostly empty space. The nucleus, despite containing almost all of the atom's mass, occupied only about 1/10,000th of the atom's volume. The atom was almost entirely empty. Rutherford is worth lingering on for a moment longer, because his personality shaped the culture of nuclear physics in ways that echo right through our story. He was enormously charismatic, with a booming laugh that could reportedly be heard from several rooms away. He ran his laboratory with a combination of fierce intellectual standards and genuine warmth toward his students. He had a famous disdain for overly theoretical physics. He once declared that if you couldn't explain your results to a barmaid, you probably didn't understand them yourself. His laboratory at the Cavendish in Cambridge became a factory of Nobel Prize winners. No fewer than 11 of his students and research associates would go on to win the Nobel Prize. And his instinct for what mattered, for which experiments would reveal something fundamental, was almost uncanny. When Geiger and Marsden reported those bizarre, backscattered alpha particles, most physicists would have shrugged and moved on. Rutherford immediately sensed that something profound was hidden in those numbers. He spent months working through the mathematics of scattering, quite unusual for a man who preferred experiments to equations. And the nuclear model of the atom emerged from that analysis. He also gave one of the most ironically wrong predictions in the history of physics. In 1933, the year the neutron was confirmed and nuclear physics was accelerating, Rutherford told a reporter that anyone who looked for a source of power in the transformation of atoms was talking moonshine. Energy from atoms, he said, was a nice dream, but utterly impractical. He died in 1937, just 2 years before fission was discovered, and just 5 years before Fermi's pile proved that nuclear energy was not moonshine at all. It's a reminder that even the greatest scientists can be spectacularly wrong about the implications of their own discoveries. And here's where the energy story starts to click into focus. Because once you know that the atom has a nucleus, you can start asking questions about what holds that nucleus together. The nucleus contains protons, positively charged particles, and they're packed together in an impossibly small space. But positive charges repel each other. The electromagnetic force pushing those protons apart is enormous at nuclear distances. So there must be some other force, something even stronger than electromagnetism, holding the nucleus together. That force, which physicists would eventually call, with characteristic lack of poetry, the strong nuclear force, is the most powerful force in nature. And the energy bound up in it, the energy required to hold a nucleus together against the electromagnetic repulsion of all those protons, is vast. That binding energy is the source of nuclear power. It's what Marie Curie's radium was tapping into. It's what makes the stars burn. And it's what human beings would eventually learn to release on demand, with consequences both miraculous and terrifying. But we're getting ahead of ourselves. In the early 19-teens, the nucleus had been discovered, but its internal structure was still mysterious. Rutherford suspected there was another particle inside the nucleus besides the proton, something electrically neutral, something with mass but no charge, that would help explain why atoms were heavier than the number of protons alone could account for. He was right, but proving it would take another 2 decades. In 1932, one of Rutherford's students, James Chadwick, finally discovered the neutron, and that discovery changed everything. Because the neutron, being electrically neutral, could approach and enter a nucleus without being repelled by its positive charge. A proton, fired at a nucleus, has to fight against the electromagnetic barrier. A neutron can just walk right in, and that property, that ability to penetrate nuclear defenses, would turn out to be the key that unlocked nuclear fission. Now, here's where the story accelerates, and where the cast of characters starts to expand in a way that feels almost like a novel. Because in the 1930s, nuclear physics was exploding, not literally, not yet, with discoveries that were coming so fast that researchers could barely keep up. Laboratories across Europe were racing to understand what happened when you bombarded different elements with neutrons. And in Rome, a brilliant, intense Italian physicist named Enrico Fermi was leading one of the most productive teams. Fermi is one of those rare figures in physics who was equally gifted at theory and experiment. Most physicists lean one way or the other, but Fermi was outstanding at both. Born in Rome in 1901, he showed extraordinary mathematical talent from childhood. He earned his doctorate at 21, became a full professor at the University of Rome at 26, and assembled a team of young physicists, the Via Panisperna boys, named after the street where their lab was located, who systematically bombarded every element they could find with neutrons to see what would happen. And they made a peculiar discovery. When they slowed the neutrons down, by passing them through paraffin wax or water before they hit the target, the nuclear reactions became more efficient. Slow neutrons were better at inducing reactions than fast ones. This seemed counterintuitive, like throwing a ball gently at a target would be more effective than hurling it. But it made sense quantum mechanically. A slow neutron spends more time near a nucleus, giving it a higher probability of being captured. Fermi figured this out in October 1934, reportedly while playing with a block of paraffin wax, and the insight would prove absolutely crucial later. Slow neutrons, moderated neutrons, as they'd come to be called, would become the key to making a sustained nuclear chain reaction possible. But here's where Fermi made an understandable mistake. When he bombarded uranium with neutrons, he got radioactive products that didn't match any known element. He assumed he had created new, heavier elements, transuranic elements, elements beyond uranium on the periodic table. The Italian press enthusiastically reported that Fermi had created new elements, and he was awarded the Nobel Prize in Physics in 1938, partly for this work. But what had actually happened in that experiment was something far stranger and far more momentous than creating new elements. What Fermi had actually done, without realizing it, was split the uranium atom in half. He had achieved nuclear fission 4 years before anyone recognized it for what it was. The recognition came from Berlin in December 1938, and the circumstances were shaped by the darkest chapter of 20th century history. Otto Hahn and Fritz Strassmann were radiochemists at the Kaiser Wilhelm Institute, methodical and precise, the kind of scientists who trusted their analytical techniques absolutely. They were bombarding uranium with neutrons, following up on Fermi's earlier experiments, and they were doing something Fermi hadn't done carefully enough: meticulous chemical analysis of every product, and they found something that made no sense. Among the reaction products was barium. Barium has an atomic number of 56. Uranium has an atomic number of 92. Barium is nowhere near uranium on the periodic table. How could adding a single neutron to uranium produce an element that was roughly half its size? It was as if you'd tossed a pebble at a boulder, and the boulder had cracked clean in two. Hahn, who was a superb and careful chemist, checked and rechecked and rechecked again. Barium was unquestionably there, but he had no physical explanation for how it could have gotten there. He was a chemist, not a nuclear physicist. He could identify the products, but explaining the mechanism was beyond his expertise. Hahn wrote a letter to his longtime collaborator, the physicist Lise Meitner, who had recently fled Nazi Germany for Sweden. Meitner was Jewish, and her position in Berlin had become untenable after Austria's annexation by Germany in March 1938. She had escaped with little more than the clothes she was wearing, smuggled across the Dutch border with the help of colleagues. Now she was in Sweden, isolated, separated from the laboratory she'd worked in for 30 years, but still thinking, still corresponding with Hahn, still very much a physicist. And it was Meitner, together with her nephew Otto Frisch, who figured out what was happening. During a Christmas visit, walking in the snowy woods near Gothenburg, they worked through the physics. They realized that Hahn's barium could only have come from one place. The uranium nucleus had split apart. It had divided into two roughly equal pieces, one of which was barium, the other krypton. And when Meitner calculated the energy released by this splitting, using Einstein's famous equation E equals mc squared, which tells you how much energy is equivalent to a given amount of mass, the number was enormous. The two fragments, barium and krypton, together weighed slightly less than the original uranium atom. The missing mass had been converted into energy, about 200 million electron volts per fission event. That's roughly 100 million times more energy than a typical chemical reaction produces. 100 million times. Frisch rushed back to Copenhagen and told Niels Bohr, who was about to leave for the United States. Bohr reportedly slapped his forehead and exclaimed something like, "Oh, what fools we have been. We should have seen this before." Frisch borrowed the term fission from biology, cell division, where a living cell splits into two, and by January 1939, The news was spreading through the physics community like wildfire. And here's where you need to understand how fast things moved, because the speed is almost dizzying. Within weeks of the fission announcement, laboratories across the world had confirmed the result. Uranium could be split. The energy released was vast, and almost immediately, physicists began asking the critical question, the question that would change the course of human history. When uranium fissions, does it release additional neutrons? Because if it does, if each fission event releases not just energy, but also 2 or 3 new neutrons, then those neutrons could go on to split other uranium atoms, which would release more neutrons, which would split more atoms, and you'd have a chain reaction. A self-sustaining, self-amplifying cascade of nuclear splitting that could release energy on an almost unimaginable scale. The person who saw this most clearly, and who saw it first, was a Hungarian physicist named Leo Szilard. And Szilard is one of the most fascinating, most prescient, and most tragically vindicated figures in this entire story. Born in Budapest in 1898, Szilard was restless, brilliant, and perpetually worried about the future. He had fled Germany in 1933, the day after the Reichstag fire, recognizing immediately what the Nazi rise to power would mean. He moved to London, then to New York, always thinking several steps ahead, always imagining worst-case scenarios, which, in the 1930s, kept turning out to be accurate. Here's the thing about Szilard. He had conceived the idea of a nuclear chain reaction years before fission was even discovered. In 1933, walking through the streets of London, reportedly at a traffic light on Southampton Row in Bloomsbury, he had a flash of insight. He'd just read a newspaper article about Rutherford, dismissing the idea of using nuclear energy as moonshine, as impractical nonsense. And standing at that traffic light, Szilard suddenly saw it. If you could find a nuclear reaction that released more neutrons than it consumed, those neutrons could trigger more reactions, which would release more neutrons, and the whole thing would amplify exponentially. A chain reaction. He filed a patent on the concept in 1934, a patent on a nuclear chain reaction, 5 years before fission was discovered, and assigned it to the British Admiralty in secret, because he was already worried about what would happen if the wrong people figured this out. So when fission was announced in January 1939, Szilard immediately grasped the implications. He rushed to Columbia University in New York, where he set up an experiment with Walter Zinn to test whether neutrons were released during uranium fission. And in March 1939, they got the answer. Yes. Each uranium fission event released, on average, about 2 to 3 additional neutrons. A chain reaction was possible. Szilard later recalled that moment with characteristic gravity. He said he knew the world was headed for grief. And here's where the story takes a turn that connects nuclear physics to world politics in the most direct and terrifying way possible. Because Szilard was not only thinking about chain reactions in the abstract, he was thinking about Nazi Germany. He knew that German physicists, Hahn, Strassmann, Heisenberg, had access to the same knowledge. He knew that Germany had seized the uranium mines of Czechoslovakia after occupying the Sudetenland, and he was terrified that the Germans might build a nuclear weapon first. Szilard decided to warn the American government, but he was a relatively unknown émigré physicist. Who would listen to him? He needed someone with credibility, someone whose name carried weight. And so he went to see Albert Einstein. In the summer of 1939, Szilard and fellow Hungarian physicist Eugene Wigner drove out to Einstein's vacation cottage on Long Island. Einstein, by this time, was the most famous scientist in the world. He had settled in Princeton in 1933 and was working on unified field theory, somewhat removed from the latest developments in nuclear physics. When Szilard explained the possibility of a chain reaction to him, Einstein reportedly said he hadn't thought of that, but he immediately understood the implications. And on August 2, 1939, Einstein signed a letter to President Franklin Roosevelt, a letter Szilard had drafted, warning that recent developments in nuclear physics might make it possible to build extremely powerful bombs of a new type, and urging the government to take action. And Szilard wasn't the only one who saw the danger. In France, Frédéric Joliot-Curie, Marie Curie's son-in-law, who had won a Nobel Prize of his own, independently confirmed that neutrons were released during fission and published his results. Szilard was furious. He had been trying to convince physicists to keep their fission results secret to avoid tipping off the Germans. But Joliot-Curie published openly, and once the genie was out of the bottle, there was no putting it back. The physics was now available to anyone who could read a scientific journal, in any country, including Germany. The race was on, whether anyone wanted it to be or not. There's a detail about the Einstein-Szilard letter that's worth knowing, because it illustrates the human side of these world-changing moments. Szilard couldn't drive. He had never learned. So when he needed to reach Einstein's cottage on Long Island, he had to convince Wigner to drive him. Wigner was busy, and they got lost trying to find the cottage in the small resort town of Peconic. They stopped and asked a young boy for directions to Einstein's house, and the boy pointed the way. Think about that. A child on a summer afternoon, casually directing two Hungarian physicists to the house where they would draft the letter that would lead to the atomic bomb. History turns on such tiny, ordinary moments. That letter, the Einstein-Szilard letter, is one of the most consequential documents of the 20th century. It didn't immediately lead to the Manhattan Project. The response was initially sluggish, bureaucratic, underfunded, but it planted the seed. It put the idea of nuclear weapons on the desk of the President of the United States. And when events accelerated, when the war began, when intelligence reports suggested the Germans might be pursuing a bomb, that seed grew into the largest, most expensive, most secret engineering project in human history. But before we get to the Manhattan Project, there's a crucial piece of the physics puzzle we need to understand, because it's directly relevant to how nuclear reactors work. Not all uranium is the same. Natural uranium comes in two main forms, or isotopes, uranium-238 and uranium-235. They're chemically identical. They have the same number of protons, the same number of electrons, but U-235 has 3 fewer neutrons in its nucleus than U-238, and that seemingly tiny difference changes everything. U-235 can be fissioned by slow neutrons. Hit it with a low-energy neutron and it splits apart readily. U-238 is much more stubborn. It tends to absorb slow neutrons without fissioning, and it requires very high-energy fast neutrons to split. The problem is that natural uranium is about 99.3% U-238 and only about 0.7% U-235. The stuff that fissions easily is incredibly rare, and separating U-235 from U-238 is extraordinarily difficult because they're chemically identical. You can't use chemical methods to sort them. The only difference is a tiny variation in mass, less than 2%. Separating them requires physical processes, gaseous diffusion, centrifuges, electromagnetic separation, that are technologically demanding, energy-intensive, and slow. The difficulty of isotope separation would become one of the central challenges of both nuclear weapons and nuclear energy. But here's the clever part, and this is where Fermi's earlier discovery about slow neutrons becomes crucial. You don't necessarily need to separate the isotopes to build a reactor. If you can slow the neutrons down enough, using a moderator, some material that slows neutrons without absorbing too many of them, then even that tiny fraction of U-235 in natural uranium can sustain a chain reaction. The moderator makes the neutrons slow. Slow neutrons are more likely to cause fission in U-235. Each fission releases more neutrons. The moderator slows those new neutrons down too, and the cycle continues. The moderator makes up for the rarity of U-235 by making every neutron more effective. And this insight, that a moderated chain reaction in natural uranium was theoretically possible, is what led to the world's first nuclear reactor. And the person who built it was Enrico Fermi. He had fled Italy in 1938, traveling to Stockholm to receive his Nobel Prize and simply never going back. His wife Laura was Jewish, and Italy had just enacted anti-Semitic racial laws. Fermi collected his Nobel Prize money, took his family to New York, and never returned to Mussolini's Italy. He ended up at the University of Chicago, recruited for the Manhattan Project, tasked with one specific, monumental goal: demonstrate that a self-sustaining nuclear chain reaction was physically possible. The experiment took place in a squash court under the bleachers of Stagg Field, the university's abandoned football stadium. Fermi's team built what they called a pile, an assembly of roughly 40,000 uranium and uranium oxide blocks, interspersed with about 385 tons of pure graphite, which served as the neutron moderator. Graphite, the same stuff in pencil lead, slows neutrons down beautifully without absorbing too many of them. The pile was constructed layer by layer, block by block, over the course of several weeks in November 1942. It had no radiation shielding. It had no cooling system. The only safety mechanism was a set of cadmium-coated control rods. Cadmium absorbs neutrons voraciously that could be inserted into the pile to soak up neutrons and kill the chain reaction. One of these was an actual emergency rod, nicknamed Zip, that was held in place by a rope running through a pulley. A man stood by with an axe, ready to cut the rope and let the rod drop into the pile if things got out of hand. That's where the expression SCRAM comes from in nuclear engineering. It stands for Safety Control Rod Axeman, or at least that's the folklore. The real origin is debated, but it's too good a story to leave out. The construction itself was a remarkable feat of improvised engineering. The uranium and graphite had to be extraordinarily pure. Even tiny amounts of impurities like boron or cadmium would absorb enough neutrons to kill the chain reaction. Fermi's team tested every batch of graphite and uranium for neutron absorption before using it. The graphite came from various manufacturers, and the quality varied enormously. Some batches were nearly pure enough, others were contaminated and had to be rejected. The uranium metal was produced by a company in Iowa, and the uranium oxide came from several sources. Every block was machined to precise dimensions and stacked according to a careful lattice pattern that Fermi had calculated would maximize the neutron multiplication factor. The pile grew layer by layer, roughly spherical in shape, about 25 feet across and 20 feet high when finished. At each stage, Fermi's team measured the neutron multiplication and compared it to his predictions. The agreement was extraordinary. Fermi's hand calculations, done without a computer, predicted the pile's behavior with remarkable accuracy. He knew, before the final control rod was withdrawn, almost exactly what would happen. On December 2, 1942, a bitterly cold day in Chicago, Fermi ordered the control rods slowly withdrawn. The neutron count on the monitoring instruments began to climb. George Weil, operating the final control rod, pulled it out in small increments, 6 inches at a time. At 3:25 in the afternoon, the instruments showed the neutron flux rising in a self-sustaining exponential increase. The pile had gone critical. A self-sustaining nuclear chain reaction was running for the first time in human history. Fermi let it run for 28 minutes, producing about half a watt of power, barely enough to light a flashlight. Then he ordered the control rods reinserted, and the reaction stopped. Arthur Compton, the physicist overseeing the project, made a famously cryptic phone call to James Conant at the National Defense Research Committee. "The Italian navigator has just landed in the New World," Compton said. "How were the natives?" Conant asked. "Very friendly," Compton replied. The age of nuclear energy had begun, in a squash court, under a football stadium, in the middle of a war. Now, the Chicago pile was a scientific proof of concept, not a power plant. It was designed to prove that a chain reaction could be controlled, not to generate useful energy. But the principles it demonstrated, moderation, controlled fission, chain reaction management, are exactly the principles that every nuclear power reactor in the world still uses today. The fuel, the moderator, the control rods. The basic architecture hasn't changed in 80 years. What's changed is the scale, the safety systems, the engineering sophistication, and the sheer amount we've learned about what can go wrong. But in December 1942, generating electricity was not the goal. Winning the war was. The Manhattan Project, officially known as the Manhattan Engineer District, was the massive secret effort to build nuclear weapons before Nazi Germany could. It was led by General Leslie Groves, a blunt, demanding Army Corps of Engineers officer who had just overseen the construction of the Pentagon, and by J. Robert Oppenheimer, a brilliant, charismatic, deeply cultured theoretical physicist from Berkeley. Groves and Oppenheimer were an unlikely pair, the burly, pragmatic general and the thin, chain-smoking intellectual who read Sanskrit poetry and once tried to poison his university tutor with an apple laced with chemicals. But they worked. Their partnership was one of the most consequential management teams in the history of technology. The Manhattan Project employed over 125,000 people at its peak. It built entire secret cities from scratch: Oak Ridge, Tennessee, for uranium enrichment, Hanford, Washington, for plutonium production, and Los Alamos, New Mexico, the isolated mountaintop laboratory where the bomb itself was designed and assembled. The total cost was about $2 billion in 1940s money, roughly equivalent to $30 billion today, and the secrecy was extraordinary. The vast majority of the workers at Oak Ridge and Hanford had no idea what they were making. They knew their jobs: operate this machine, monitor this gauge, follow this procedure, but not the larger purpose. Entire factories employing tens of thousands of people were devoted to producing material whose function was classified. At Oak Ridge, the primary mission was uranium enrichment, separating the fissile U-235 from the far more abundant U-238. Multiple methods were pursued simultaneously because nobody was sure which would work best. Gaseous diffusion involved converting uranium into uranium hexafluoride gas and pumping it through thousands of barriers with microscopic pores. The slightly lighter U-235 molecules diffused through the pores a tiny bit faster than U-238 molecules. Each pass produced only a minuscule enrichment, so the gas had to be cycled through thousands of stages in enormous cascading plants. The K-25 gaseous diffusion plant at Oak Ridge was, at the time of its construction, the largest building in the world. A U-shaped structure over half a mile long. Electromagnetic separation, using massive magnets to deflect uranium ions along slightly different paths based on their mass, was pursued at the Y-12 plant. Both methods were energy-intensive, expensive, and painfully slow. Producing enough enriched uranium for a single bomb took the better part of a year. At Hanford, the approach was different. Instead of enriching uranium, they built massive nuclear reactors, the first production-scale reactors in history, to transmute uranium-238 into plutonium-239. Here's how that works, and it's genuinely clever. When U-238 absorbs a neutron without fissioning, it becomes U-239, which is unstable and undergoes two successive beta decays, each one converting a neutron in the nucleus into a proton by emitting an electron. After those two decays, you have a new element with 94 protons, element 94, plutonium. And plutonium-239, like U-235, is fissile. It can sustain a chain reaction. It can fuel a bomb. And crucially, because plutonium is a different element from uranium, it can be separated chemically, which is far easier than the physical isotope separation required for U-235 enrichment. So you run a reactor. You irradiate natural uranium. Some of the U-238 converts to plutonium, and then you chemically extract the plutonium from the spent fuel. The Hanford reactors were designed to do exactly this, on an industrial scale, cooling the cores with water pumped from the Columbia River. At Los Alamos, Oppenheimer assembled arguably the greatest concentration of scientific talent ever gathered in one place. Hans Bethe led the theoretical division. Edward Teller worked on hydrodynamics. Richard Feynman, still in his 20s, computed bomb physics on primitive mechanical calculators. Enrico Fermi was a regular consultant. The British delegation included Rudolf Peierls and Klaus Fuchs, who would later be revealed as a Soviet spy. The intellectual firepower was staggering, and the atmosphere was a strange mixture of academic seminar and military urgency. Brilliant physicists arguing about neutron cross-sections and implosion dynamics, while military police patrolled the perimeter and all outgoing mail was censored. The social life at Los Alamos was surreal. Here was this isolated mesa in the New Mexico desert, surrounded by barbed wire and armed guards, populated by some of the most brilliant people in the world and their families. There were square dances, poker games, and parties. Oppenheimer's wife, Kitty, mixed cocktails, while Nobel laureates discussed the finer points of neutron cross-sections. Children played in the canyons, while their parents designed weapons of unprecedented destructive power. Nobody could tell their families what they were really doing. The address for everyone at Los Alamos was simply P.O. Box 1663, Santa Fe, New Mexico. Babies born at the laboratory had their birth certificates list their place of birth as P.O. Box 1663, which caused bureaucratic confusion for decades afterward. The work itself was grueling. Teams worked around the clock, often sleeping on cots in their offices. The computational challenges were enormous. Remember, this was the era before electronic computers. Most calculations were done by hand or on mechanical desk calculators, or by teams of human computers, often the physicists' wives, working through numerical problems step by step. Feynman organized these computing teams with characteristic cleverness, setting up relay systems where each person would perform one step of a calculation and pass the result to the next person, creating a kind of human assembly line for mathematics. It was tedious, exhausting work, and mistakes could be deadly. Not in the abstract sense, but literally, as several researchers experienced accidental radiation exposures from criticality experiments, two of which proved fatal in 1945 and 1946. The technical challenge was immense. For the uranium bomb, the design was relatively straightforward. A gun-type weapon where one subcritical mass of enriched uranium was fired into another to create a supercritical assembly. They were so confident in this design that it was never tested before use. The plutonium bomb was much trickier because plutonium has a higher rate of spontaneous fission that would cause the assembly to pre-detonate and fizzle. The solution was implosion, surrounding a sphere of plutonium with precisely shaped explosive lenses that would compress it simultaneously from all sides, driving it to supercritical density in microseconds. Getting the implosion to be sufficiently symmetrical was one of the most difficult engineering challenges of the entire project. The implosion design was tested on July 16, 1945, in the Trinity test, at a remote site in the New Mexico desert called Jornada del Muerto, the Journey of the Dead Man. The fireball was visible from 150 miles away. The mushroom cloud rose to over 12 kilometers. The blast created a crater of radioactive glass, melted sand fused by the heat, that was later named trinitite. The yield was about 21 kilotons of TNT equivalent. Oppenheimer famously recalled a line from the Hindu scripture, the Bhagavad Gita, "Now I am become death, the destroyer of worlds." Kenneth Bainbridge, the test director, was more blunt. He turned to Oppenheimer and said, "Now we are all sons of bitches." 3 weeks later, on August 6, 1945, the uranium gun-type bomb, named Little Boy, was dropped on Hiroshima, Japan. 3 days after that, on August 9th, the plutonium implosion bomb, named Fat Man, was dropped on Nagasaki. The combined death toll was approximately 210,000 people by the end of 1945, with tens of thousands more dying in subsequent years from radiation-related illnesses. The victims were overwhelmingly civilians. The ethical questions raised by these bombings have never been resolved, and probably never will be. They remain among the most debated moral decisions in human history. Those who defend the bombings argue that they ended the war and prevented a land invasion of Japan that would have cost millions of lives on both sides. Those who oppose them argue that the deliberate targeting of civilian populations with weapons of mass destruction is wrong, regardless of the strategic calculus, and that Japan was already on the verge of surrender. The debate continues. It should continue. These are questions that deserve to be revisited by every generation because the technology hasn't gone away. And this is where our story pivots. Because after the war, after the horror of Hiroshima and Nagasaki, there was a profound and very human impulse to find a redemptive purpose for nuclear energy. The same physics that had leveled 2 cities could, in theory, generate electricity for millions of homes. The same chain reaction that powered a weapon of mass destruction could, if properly controlled, boil water and spin turbines and light up the night. And the question that dominated the late 1940s and the 1950s was whether this terrible power could be tamed, domesticated, turned toward peaceful purposes, whether the atom could be made a servant rather than a destroyer. The early post-war years were dominated by secrecy and military control. The United States Atomic Energy Commission, created by the Atomic Energy Act of 1946, took over the Manhattan Project's facilities and maintained a government monopoly on nuclear technology. The Soviet Union, aided by espionage, Klaus Fuchs had been passing detailed bomb designs to Soviet intelligence throughout the Manhattan Project, detonated its own nuclear weapon in August 1949, far earlier than American intelligence had predicted. Britain followed in 1952, France in 1960, China in 1964. The nuclear arms race was on, and the Cold War cast a shadow over everything nuclear. But in December 1953, President Dwight Eisenhower stood before the United Nations General Assembly and delivered a speech that would reshape the trajectory of nuclear technology. The speech was called Atoms for Peace, and it was remarkable, both as rhetoric and as policy. Eisenhower proposed that nations contribute fissile material to a new international agency, which would become the International Atomic Energy Agency, the IAEA, and that this material be used for peaceful purposes, particularly the generation of electrical power. "The United States pledges before you," Eisenhower said, "and therefore before the world, its determination to help solve the fearful atomic dilemma, to devote its entire heart and mind to find the way by which the miraculous inventiveness of man shall not be dedicated to his death, but consecrated to his life." It was a powerful speech, and it had real consequences. It opened the door for civilian nuclear power development worldwide. The United States began sharing nuclear technology with allied nations. Research reactors sprang up at universities around the world, and the race to build the first nuclear power plant, a reactor designed specifically to generate electricity for the civilian grid, began in earnest. Now, the first reactor to generate electricity was actually an experimental reactor called EBRI, the Experimental Breeder Reactor, at the Idaho National Laboratory. On December 20th, 1951, it produced enough electricity to light 4 light bulbs. It was a proof of concept, not a power plant. The first nuclear power plant to feed electricity into a civilian grid was the Obninsk nuclear power plant in the Soviet Union, which began operating on June 27, 1954, producing about 5 megawatts of electrical power. It was small by later standards, but it was real. Nuclear-generated electricity flowing into the grid, powering homes and factories. In Britain, the Calder Hall reactor at Sellafield began operating in 1956, and it was scaled up to commercial levels. In the United States, the Shippingport Atomic Power Station in Pennsylvania began operating in 1957, the country's first full-scale commercial nuclear power plant. It was designed by Admiral Hyman Rickover's team, the same Rickover who had pioneered the use of nuclear reactors to power submarines, creating the nuclear navy that would become one of the most strategically important military programs of the Cold War. And this is worth pausing on for a moment, because the submarine connection is more important than you might think. Rickover, a brilliant, abrasive, demanding naval officer. He once kept a candidate for his program waiting outside his office for 8 hours, then dismissed him in 3 minutes. Rickover had driven the development of the first nuclear submarine, the USS Nautilus, which was launched in 1954. The reactor that powered the Nautilus used pressurized water as both its moderator and coolant, what's called a pressurized water reactor, or PWR. The water flows through the reactor core under high pressure, absorbing heat from the nuclear fuel without boiling, then transfers that heat to a secondary water loop through a steam generator. The secondary loop boils, producing steam that drives turbines. This design was chosen for submarines because it was compact, reliable, and well understood. And when Rickover's team was tasked with building Shippingport, they essentially scaled up the submarine reactor design for land-based power generation. That decision, to use the pressurized water reactor design for America's first civilian nuclear plant, had enormous long-term consequences. Because once Shippingport proved the PWR concept, the design became the template. Westinghouse, the company that had built the Nautilus reactor, commercialized the PWR design for land-based power plants. General Electric took a slightly different approach, developing the boiling water reactor, or BWR, where the water in the reactor core is allowed to boil directly, and the steam goes straight to the turbines without a secondary loop. Both designs use ordinary light water, regular H2O, as both moderator and coolant. And between them, PWRs and BWRs account for the vast majority of the world's nuclear power plants today. The reactor designs we're running in the 21st century are, in a real sense, descended from a submarine engine designed in the early 1950s. That submarine heritage is why the dominant reactor designs look the way they do. Not because they're the theoretically optimal designs for civilian power generation, but because they were the designs the Navy had already proven to work. And there were other designs, other approaches, some of them arguably better in various ways. The Canadian CANDU reactor, developed in the 1960s, uses heavy water, deuterium oxide, where the hydrogen atoms have an extra neutron, as its moderator and coolant. Heavy water is a more effective moderator than light water, which means CANDU reactors can use natural uranium as fuel, without any enrichment at all. That's a significant advantage in terms of fuel supply and non-proliferation. The British developed gas-cooled reactors, using carbon dioxide gas as the coolant and graphite as the moderator. The Soviet Union developed the RBMK reactor, a graphite-moderated, water-cooled design that could use natural uranium and could be refueled while running, a feature that was operationally convenient, but, as the world would discover in 1986, came with catastrophic safety vulnerabilities. Let's take a moment to understand how a nuclear power reactor actually works, step by step, because the engineering is genuinely elegant once you see it. At its core, no pun intended, a nuclear power plant is a very sophisticated way to boil water. That's it. The nuclear reaction generates heat. The heat boils water. The steam spins a turbine. The turbine drives a generator. Electricity comes out the other end. The back half of the process, steam, turbine, generator, is identical to a coal plant or a natural gas plant. The only difference is the heat source. Instead of burning fossil fuels, you're splitting atoms. But that heat source is extraordinarily concentrated. A single nuclear fuel pellet, about the size of a pencil eraser, contains as much energy as a ton of coal. A typical reactor core contains tens of millions of these pellets, arranged in fuel rods bundled into fuel assemblies, immersed in water inside a massive steel pressure vessel. The fuel itself is usually uranium dioxide, a ceramic material that can withstand extremely high temperatures without melting. The uranium is slightly enriched, typically to about 3 to 5% U-235, up from the natural 0.7%. This low enrichment is enough for a chain reaction in a light water reactor, but is far, far below the 90% or more enrichment needed for a weapon. That distinction matters enormously for non-proliferation. The fuel in a nuclear power plant cannot be used to make a bomb without extensive further processing. The water in the reactor serves double duty. It's both the moderator, slowing neutrons down to increase fission probability, and the coolant, carrying heat away from the fuel. In a pressurized water reactor, the water in the primary loop is kept under such high pressure, about 150 atmospheres, that it can reach temperatures above 300 degrees Celsius without boiling. This superheated water flows through a steam generator, where it transfers its heat to a separate secondary water loop that does boil, producing the steam that drives the turbines. The two loops are physically separate, which means that radioactive water from the reactor core never reaches the turbines. In a boiling water reactor, the design is simpler. The water boils directly in the reactor vessel, and the resulting steam goes straight to the turbines. This eliminates the need for a steam generator, but means the turbine hull must be treated as a potentially contaminated area. Through the 1960s and 70s, nuclear power expanded rapidly. It was the era of optimism, of grand promises. Lewis Strauss, the chairman of the Atomic Energy Commission, had famously predicted in 1954 that nuclear electricity would eventually be too cheap to meter. That prediction was wildly wrong. Nuclear power plants turned out to be enormously expensive to build, though relatively cheap to operate once running. But the sentiment captured the mood of the time. Nuclear energy was the future. It was clean. It was modern. It was practically limitless. Country after country built nuclear plants. France, with few fossil fuel resources of its own, committed to nuclear power on a massive scale, eventually generating about 75% of its electricity from nuclear reactors. Japan, similarly resource-poor, built a fleet of reactors along its coastlines. By the late 1970s, there were over 200 nuclear power reactors operating worldwide, and more were being built every year. The industry seemed unstoppable. But beneath the surface, concerns were growing. Safety questions that had been brushed aside or managed quietly were about to erupt into public consciousness in the most dramatic way possible. Because on March 28, 1979, something went very wrong at a nuclear power plant on an island in the Susquehanna River in central Pennsylvania. 3 Mile Island. The name itself has become synonymous with nuclear fear, at least in the United States. And what actually happened there is worth understanding in detail, because it illustrates something fundamental about the relationship between complex engineering systems and human error. 3 Mile Island Unit 2 was a pressurized water reactor built by Babcock and Wilcox that had been operating commercially for only about 3 months when the accident began. At about 4 o'clock in the morning on March 28th, a routine maintenance operation caused the feedwater pumps, the pumps that supply cooling water to the steam generators, to trip and shut down. This was not, in itself, a crisis. The reactor's safety systems responded as designed. The turbine tripped. The reactor scrammed, meaning the control rods dropped into the core to stop the chain reaction. So far, everything was working. But here's the thing about a nuclear reactor that makes it different from a coal plant or a gas plant. Even after you shut down the chain reaction, the fuel is still generating heat. This is called decay heat, and it comes from the radioactive decay of fission products in the fuel. In the first few seconds after shutdown, decay heat is about 7% of the reactor's full power output. For a reactor producing 900 megawatts, that's over 60 megawatts of heat with nowhere to go. And it takes hours, even days, for decay heat to diminish to negligible levels. So you must keep cooling the core, even after the reactor has been shut down. Stop cooling it, and the fuel can overheat, melt, and release radioactive material. When the feedwater pumps failed at 3 Mile Island, a relief valve on top of the pressurizer, a component that maintains pressure in the primary coolant loop, opened to release excess pressure. This was also by design, but the valve was supposed to close again once the pressure dropped to the right level. It didn't. The valve stuck open, though the indicator light in the control room showed it as closed. There was no direct indication of the valve's actual position. The light only showed whether the signal to close the valve had been sent, not whether the valve had actually closed. This was a critical design flaw. The operators, looking at their instruments, believed the valve was closed. In reality, it was wide open, and reactor coolant, pressurized, superheated water, was streaming out through it and into a drain tank on the containment floor. As coolant drained away, the pressure in the primary loop dropped. The emergency core cooling system activated automatically, pumping fresh water into the core, but the operators, confused by contradictory instrument readings and trained to worry about a different scenario, an overpressure event rather than a loss of coolant event, actually overrode the emergency cooling system and reduced its flow. They thought the core was too full of water when in fact it was losing water rapidly. They were reading the pressurizer level, which was rising because the remaining water was flashing to steam and expanding, and interpreting it as a sign that there was too much water. There wasn't too much water. There was far too little. The accident at 3 Mile Island was, in many ways, a textbook case of how complex systems fail, not through a single dramatic malfunction, but through a cascade of small problems, design flaws, and human misunderstandings that feed on each other. The Swiss cheese model of accident causation, where multiple layers of defense each have holes, and disaster occurs when the holes line up. 3 Mile Island is one of the examples that model was practically designed to explain. Consider the control room. It was state-of-the-art for the 1970s, which means it had over 100 alarms going off simultaneously during the crisis. The operators were drowning in information, much of it contradictory. One alarm would indicate high pressure, while another indicated low level. The printer logging alarm events fell so far behind that it was printing alarms from hours earlier. The operators were making decisions based on incomplete, misleading data under extreme stress in the middle of the night, and they were making those decisions based on training that hadn't prepared them for this specific combination of failures. They had been trained to worry about certain scenarios, overpressure events, loss of coolant, but the actual accident combined elements of both in a way that confused their mental models of what was happening. Over the next several hours, a significant portion of the reactor core was uncovered. The fuel rods, which must be submerged in water at all times, were exposed to steam. Without water cooling, the fuel overheated. The zirconium alloy cladding on the fuel rods reacted with steam at high temperatures, producing hydrogen gas and more heat. About half the core melted. Radioactive gases and some radioactive water were released into the environment, though in relatively small quantities. There were no immediate deaths or injuries from the accident. Studies conducted over the following decades found no measurable increase in cancer rates among the surrounding population, though this remains debated, and the subject causes understandable anxiety among people who lived nearby. But the psychological and political impact was enormous. The partial meltdown at 3 Mile Island terrified the American public. It came just 12 days after the release of a Hollywood film called The China Syndrome, starring Jane Fonda, which depicted a fictional nuclear accident at a power plant. The coincidence amplified public fear dramatically. Anti-nuclear sentiment surged. Public trust in the nuclear industry and in the government agencies that regulated it plummeted. No new nuclear power plants were ordered in the United States after 1978, and many that were under construction were canceled. The American nuclear industry, which had seemed unstoppable just a few years earlier, essentially ground to a halt. 3 Mile Island was a wake-up call. It revealed that the nuclear industry had been dangerously overconfident about safety. The instrumentation in the control room was inadequate. The operator training was insufficient. The culture of safety, the deep, institutional commitment to anticipating and preventing failures, was not where it needed to be. The accident led to sweeping reforms: the creation of the Institute of Nuclear Power Operations, major upgrades to control room design, improved training programs, new regulatory requirements. In many ways, 3 Mile Island made the nuclear industry safer, but the damage to public perception was done, and it would never fully recover in the United States. And then, 7 years later, came the disaster that made 3 Mile Island look like a minor hiccup. April 26, 1986. Chernobyl nuclear power plant, northern Ukraine, then part of the Soviet Union. And what happened there was not a partial meltdown contained within a building. It was the worst nuclear accident in history, a catastrophe of almost incomprehensible scale, and it resulted from a toxic combination of flawed reactor design, institutional arrogance, and a safety culture so dysfunctional that operators deliberately disabled multiple safety systems while conducting an unauthorized experiment on a reactor that was in an unstable condition. The Chernobyl plant used RBMK reactors, that Soviet graphite-moderated, water-cooled design we mentioned earlier. And the RBMK had a particular design flaw that would prove fatal. It had a positive void coefficient of reactivity. That's a technical term that means something very dangerous. In most Western reactor designs, if the coolant water boils and turns to steam, creating voids in the coolant, the reactivity decreases. The reactor slows down. It's a built-in safety feature, a negative feedback loop. But in the RBMK, because of the way the graphite moderator and the water interacted, boiling actually increased reactivity. More steam meant more neutron moderation by the graphite, which meant more fission, which produced more heat, which caused more boiling, which increased reactivity further. A positive feedback loop, a vicious circle. Under certain conditions, the RBMK could become a runaway system. The accident happened during a test. The plant's engineers wanted to see whether, during a power outage, the spinning turbine could generate enough electricity to bridge the gap until emergency diesel generators started up. This was actually a legitimate safety question, but the way the test was conducted was reckless, almost beyond belief. They had to reduce the reactor's power level for the test, and in doing so, they inadvertently poisoned the reactor with a fission product called xenon-135, which is a powerful neutron absorber. The reactor's power dropped far lower than intended, to nearly zero. To recover, the operators pulled out almost all of the control rods, far more than safety rules allowed. They were essentially running the reactor with almost no margin for control, in an inherently unstable configuration, with several automatic safety systems deliberately disabled so they wouldn't interfere with the test. At 1:23 in the morning, on April 26th, when they initiated the test procedure, the reactor's power surged uncontrollably. In less than a second, the power output spiked to perhaps 100 times the reactor's normal maximum. The fuel shattered. The cooling water flashed instantly to steam. The resulting steam explosion blew the 1,000-ton reactor lid off the top of the building and exposed the graphite moderator to air. The graphite caught fire. The burning graphite sent a plume of radioactive material high into the atmosphere, carried by the wind across northern Europe and eventually around the world. 2 plant workers died immediately in the explosions. 28 emergency responders, mostly firefighters, died within months from acute radiation syndrome, the lethal effects of massive radiation exposure on the human body. They had gone onto the roof of the reactor building to fight the graphite fire, not fully understanding what they were being exposed to. Some received radiation doses hundreds of times the lethal threshold. Their deaths were agonizing and prolonged, as the radiation systematically destroyed their bone marrow, their gastrointestinal tracts, their immune systems. We should state that plainly and with respect. These were people doing their jobs, responding to an emergency, and they paid for institutional failures with their lives. The broader consequences were vast. An exclusion zone of 30 kilometers was established around the plant. The nearby city of Pripyat, built specifically to house the plant's workers and their families, was evacuated. About 49,000 people left their homes, many of them forever. Eventually, over 300,000 people were relocated from contaminated areas in Ukraine, Belarus, and Russia. The long-term health effects are still debated and studied. The World Health Organization estimates that the total additional cancer deaths from Chernobyl radiation exposure may eventually number in the low thousands, though some organizations estimate higher. The full human cost, including the psychological trauma, the disrupted lives, the contaminated land that will remain uninhabitable for centuries, is incalculable. The fire burned for about 10 days. Helicopters dropped thousands of tons of sand, lead, clay, and boron on the exposed reactor core in an attempt to smother the fire and absorb neutrons. Thousands of military reservists, miners, and construction workers, collectively called liquidators, were brought in to clean up the contamination. Many of them worked in conditions of extreme radiation exposure, shoveling radioactive graphite off rooftops in shifts of just 90 seconds each, because that was the maximum exposure time allowed. An estimated 600,000 liquidators participated in the cleanup over the following years. Many received significant radiation doses, and the long-term health consequences for this group have been extensively studied and debated. A massive concrete structure, dubbed the sarcophagus, was hastily built over the destroyed reactor to contain the remaining radioactive material. It was constructed in just 6 months, under extraordinary radiation conditions, and it was never intended to be permanent. By the 2000s, the sarcophagus was deteriorating, and an enormous new confinement structure, the new safe confinement, was designed and built. This is a stainless steel arch, the largest movable structure ever built, measuring over 100 meters tall and 250 meters wide. It was assembled adjacent to the reactor and slid into place on rails in 2016. It's designed to last at least 100 years, during which the old sarcophagus and the reactor remains underneath will be dismantled. Chernobyl was a devastating blow to the global nuclear industry. It confirmed every fear the anti-nuclear movement had ever articulated. If 3 Mile Island had shaken public confidence, Chernobyl shattered it. Countries that had been building nuclear plants slowed or stopped construction. Italy shut down its entire nuclear program after a referendum. Several other European nations began planning phase-outs. The Soviet Union itself, which had been expanding nuclear power aggressively, was forced to confront the catastrophic consequences of its own institutional failures. Mikhail Gorbachev later said that Chernobyl was perhaps the real cause of the collapse of the Soviet Union. Not directly, but because it exposed the lies, the cover-ups, the dysfunctional system of governance that had made such a disaster possible. And yet, nuclear power didn't die. And this is one of the most interesting parts of the story, because it speaks to the fundamental tension at the heart of nuclear energy, the tension between its undeniable dangers and its undeniable advantages. Because here's the reality that nuclear power's advocates have always pointed to, and it's a powerful argument. Nuclear power produces electricity without emitting carbon dioxide. In a world where climate change poses an existential threat, a proven source of large-scale, reliable, carbon-free electricity is not something you can easily dismiss. A single nuclear plant can generate a gigawatt of continuous, baseload power, enough for 1 million homes, on a footprint of a few square kilometers, running day and night, rain or shine, regardless of whether the wind is blowing. Solar and wind are growing rapidly, and they're essential parts of the energy transition, but they're intermittent. They need backup. They need storage, and at the scale required to decarbonize the entire global economy, every low-carbon energy source has a role to play. France demonstrated this decades ago. By committing to nuclear power in the 1970s, France built a fleet of 56 reactors that today generate about 70% of the country's electricity. As a result, France has some of the lowest per capita carbon emissions from electricity generation in the developed world, and some of the cheapest electricity in Europe. It's a real-world existence proof that nuclear power, when managed competently, can deliver massive amounts of clean energy safely and economically over decades. But the economics have been a problem. Building a new nuclear power plant is enormously expensive. The capital costs are high, the construction times are long, and projects have a history of running over budget and behind schedule. The 2 European pressurized reactors being built in the 2010s and 2020s Olkiluoto 3 in Finland and Flamanville 3 in France. Both experienced extraordinary delays and cost overruns. Olkiluoto 3, originally expected to cost about €3 billion and be finished in 2009, wasn't completed until 2023 and cost roughly €11 billion. In the United States, the Vogtle expansion in Georgia, 2 new AP1000 reactors, similarly experienced massive delays and cost overruns, with the final cost exceeding $30 billion for the 2 units, roughly double the original estimate. These are real problems. They're not arguments against the physics of nuclear energy. The physics works fine. They're arguments about the current state of nuclear engineering and construction, and they've led to a significant rethinking of how nuclear power plants should be built. Which brings us to the most exciting development in nuclear energy in decades: small modular reactors, or SMRs. The idea behind SMRs is straightforward and appealing. Instead of building enormous, bespoke, one-of-a-kind reactor plants on site, which is what the traditional approach has been, and which is largely responsible for the cost overruns and delays, you build small, standardized reactor modules in a factory, ship them to the site, and install them. The reactors are smaller, typically producing somewhere between 50 and 300 megawatts of electrical power, compared to the 1,000+ megawatts of a conventional large reactor. Being smaller, they're simpler. Many SMR designs incorporate passive safety features, systems that rely on natural forces like gravity, convection, and the expansion of materials with heat, rather than active pumps and valves that require electrical power. Some designs can't melt down by physics, because they're designed so that as the fuel heats up, the nuclear reaction naturally slows down and stops, without any operator intervention or safety system activation. Several countries are pursuing SMR development. Russia launched the academic Lomonosov, a floating nuclear power plant based on 2 small reactors mounted on a barge, which began operating in 2020. China connected its high-temperature gas-cooled pebble bed reactor, the HTRPM, to the grid in 2023. In the United States, companies like NuScale, X-Energy, TerraPower, and Kairos Power are developing various SMR designs, some using conventional light water, others using molten salt, liquid metal, or gas coolants. NuScale received the first-ever design certification from the U.S. Nuclear Regulatory Commission for an SMR in 2023, though its first planned deployment project was subsequently canceled due to rising cost estimates. A sobering reminder that the economics of nuclear power remain challenging even for new designs. TerraPower, backed by Bill Gates, is developing a sodium-cooled fast reactor called Natrium. It's being built in Kemmerer, Wyoming, on the site of a retired coal plant, and it's designed to include integrated thermal energy storage that can boost its electrical output during periods of peak demand. The sodium coolant operates at atmospheric pressure, unlike the highly pressurized water in conventional reactors, which eliminates the risk of a high-pressure coolant leak. But sodium has its own challenges. It burns on contact with air and reacts violently with water, so the engineering around sodium handling is demanding. The appeal of SMRs goes beyond just cost and safety. Their smaller size makes them suitable for applications where a gigawatt-scale reactor simply won't fit. Remote communities that currently rely on diesel generators, industrial facilities that need process heat as well as electricity, military bases that need energy independence, retired coal plant sites that already have transmission infrastructure, and trained workforces. Several SMR developers are specifically targeting these niches, arguing that nuclear doesn't have to be one-size-fits-all anymore. There are also more exotic reactor concepts in development that go beyond conventional uranium fuel cycles. Molten salt reactors, which use nuclear fuel dissolved directly in liquid fluoride or chloride salts rather than solid fuel rods, have potential safety advantages. If the reactor overheats, a frozen salt plug at the bottom melts, and the entire fuel drains by gravity into a passively cooled storage tank. The reactor literally shuts itself down by melting its own drain plug. Oak Ridge National Laboratory actually built and operated a small molten salt reactor in the 1960s, the molten salt reactor experiment, proving the concept worked. But the program was canceled in favor of conventional designs, and the technology has been dormant for decades. It's now being revived by several startups who see in it the potential for a fundamentally different kind of nuclear reactor, one that can burn a wider range of fuels, produce less long-lived waste, and operate at higher temperatures that enable more efficient electricity generation and industrial applications like hydrogen production. And then there's fusion. Nuclear fusion, the process that powers the sun and the stars, where light atomic nuclei are forced together to form heavier ones, releasing enormous energy in the process. Fusion is the opposite of fission. Instead of splitting heavy atoms apart, you're forcing light atoms together. And if it could be made to work on Earth, at a commercial scale, it would be the ultimate energy source, essentially unlimited fuel from hydrogen isotopes in seawater, no long-lived radioactive waste, no risk of meltdown, no weapons proliferation concerns. The physics of fusion has been understood since the 1920s, when Arthur Eddington and others proposed that the sun generates energy by fusing hydrogen into helium. Hans Bethe worked out the detailed reaction chains in 1939, winning a Nobel Prize for it. And ever since the hydrogen bomb demonstrated that fusion could be achieved in an uncontrolled way, in the early 1950s, physicists and engineers have been trying to achieve controlled fusion. The challenge is staggering. To fuse hydrogen nuclei, you have to overcome the electromagnetic repulsion between their positive charges, and that requires temperatures of over 100 million degrees Celsius, roughly 10 times hotter than the center of the sun. At those temperatures, matter exists as plasma, a state where electrons are stripped from atoms, and confining that plasma is extraordinarily difficult. You can't put it in a container, because no material can withstand those temperatures. Instead, you have to confine it using magnetic fields or inertial forces. The quest for controlled fusion is, in many ways, the ultimate engineering challenge. Think about what you're trying to do. You need to create conditions hotter than the center of the sun, over 100 million degrees Celsius, and maintain them long enough and at high enough density for the hydrogen nuclei to overcome their mutual electromagnetic repulsion and fuse together. At those temperatures, all matter exists as plasma, a state where electrons have been stripped away from atoms and everything is an electrically charged gas. You can't contain plasma in any ordinary vessel. It would vaporize any material it touched instantly. So you have to contain it, using magnetic fields, shaping invisible magnetic bottles that hold the superheated plasma in place while it reacts. The tokamak, which is the most developed approach, creates a donut-shaped magnetic cage using a combination of external magnets and an electrical current running through the plasma itself. The plasma spirals around inside this magnetic donut, confined by the field, heated by microwaves and neutral beam injection, and, if everything works, fusing hydrogen isotopes and releasing energy in the process. The challenge is that plasma is extraordinarily difficult to control. It's turbulent, unstable, and constantly trying to escape its magnetic confinement, the way water tries to escape through any gap in a bucket. Physicists have been gradually taming these instabilities for decades, each generation of tokamak lasting a little longer and reaching a little higher temperature, but the gap between laboratory demonstrations and a practical power plant remains significant. The two main approaches to magnetic confinement fusion are the tokamak and the stellarator. The tokamak, a Russian invention from the 1950s, the name is a Russian acronym, uses a donut-shaped magnetic field to confine the plasma. ITER, the International Thermonuclear Experimental Reactor, being built in Cadarache, France, is the world's largest tokamak, a massive international collaboration involving 35 countries and costing over 20 billion euros. It's designed to produce 500 megawatts of fusion power from 50 megawatts of heating power, a gain factor of 10, which would be a historic first. But ITER has faced decades of delays and cost overruns. Originally planned to begin fusion experiments around 2020, the current timeline has first plasma pushed back significantly, with full fusion power not expected until the mid-2030s at the earliest. Meanwhile, a new wave of private fusion companies has emerged, some of them pursuing approaches quite different from the traditional tokamak. Commonwealth Fusion Systems, spun out of MIT, is building a compact tokamak called Spark that uses high-temperature superconducting magnets, a breakthrough in magnet technology that allows much stronger magnetic fields in a smaller device. TAE Technologies is pursuing a different plasma confinement approach. Helion Energy is developing a pulsed fusion system. In December 2022, the National Ignition Facility at Lawrence Livermore National Laboratory achieved scientific energy break-even in a laser-driven inertial confinement fusion experiment. For the first time, a fusion reaction produced more energy than the lasers delivered to the fuel. It was a milestone, though the experiment was far from practical power generation, as the lasers themselves consumed far more energy than they delivered. The running joke in fusion research has always been that commercial fusion power is 30 years away, and has been 30 years away for the last 60 years. That joke is less funny than it used to be, partly because some of the private companies are now making aggressive timelines and have genuine technical achievements to point to, and partly because the urgency of climate change has made the stakes much higher. Whether fusion will arrive in time to contribute meaningfully to decarbonization is an open question. Most serious projections don't have commercial fusion electricity before the late 2030s at the very earliest, and many are skeptical even of that. But the science is advancing, the engineering challenges are being chipped away at, and the potential payoff is so enormous that the effort seems justified. So where does that leave nuclear power today, as you lie there, letting all of this settle? It leaves it in a genuinely interesting and contested place. For years, even decades, nuclear energy seemed to be in permanent decline. Aging reactors being decommissioned, few new ones being built, public opposition strong, costs high. But something has shifted in the last few years, and it has everything to do with climate change. The Intergovernmental Panel on Climate Change, the IPCC, has consistently included nuclear power in its scenarios for limiting global warming to 1.5 or 2 degrees Celsius. Their models generally show nuclear energy expanding, not contracting, in a decarbonized world. The argument is simple and hard to dismiss. We need every low-carbon tool we can get, and nuclear is the one that already exists at scale, that generates reliable baseload power, and that has an 80-year track record of operation. Yes, it has risks. Yes, it has costs. But so does every energy source. And the risk of climate change, the cost of not decarbonizing fast enough, dwarfs the risks of nuclear power by any reasonable accounting. Several countries have reversed their nuclear phase-outs or announced new nuclear ambitions. Japan, which shut down its entire nuclear fleet after the Fukushima accident in 2011, when a massive earthquake and tsunami caused meltdowns at 3 reactors, leading to the evacuation of over 150,000 people. Japan has begun restarting some of its reactors, recognizing that it cannot meet its climate commitments without them. The Fukushima accident, which we should mention with the same gravity as 3 Mile Island and Chernobyl, was caused not by operator error or design flaws in the reactors themselves, but by an external event, a magnitude 9.0 earthquake, the most powerful ever recorded in Japan, followed by a tsunami with waves over 14 meters high that overwhelmed the plant's seawalls and flooded the backup diesel generators needed to power the emergency cooling systems. Without cooling, 3 of the 6 reactors suffered meltdowns. It was a catastrophe, and it prompted a worldwide reassessment of nuclear safety, particularly regarding the vulnerability of plants to extreme natural events. No one died from direct radiation exposure at Fukushima, though 1 worker died years later from lung cancer attributed to radiation. But the evacuation itself caused significant hardship and, by some estimates, contributed to over 2,000 stress-related deaths among elderly evacuees. The economic costs have been staggering, with cleanup expected to take decades and cost hundreds of billions of dollars. Fukushima reinforced a crucial lesson. Even well-designed reactors can fail when faced with external threats that exceed their design basis. Safety is not just about the reactor, it's about the whole system, including the site, the natural hazards, the backup systems, and the preparedness for events that have never happened before. But even with Fukushima's lessons still fresh, the world is reconsidering nuclear. China is building more nuclear reactors than any other country, over 20 units under construction as of the mid-2020s, with plans for many more. India is expanding its nuclear fleet. The United Kingdom has committed to new nuclear construction, including the Hinkley Point C reactor in Somerset, a large EPR design, and is investing in SMR development. Poland, which has no nuclear power plants, has announced plans to build its first. Even countries like the Netherlands and Sweden, which had previously moved away from nuclear, have signaled renewed interest. And there's a wild card that nobody saw coming. The explosive growth of artificial intelligence and data centers has created enormous new demand for electricity. Clean, reliable, always-on electricity. Tech companies like Microsoft, Google, and Amazon have signed agreements with nuclear energy providers to power their data centers. Microsoft made headlines by announcing a deal to help restart a unit at 3 Mile Island. Yes, that 3 Mile Island, Unit 1, which was a separate, undamaged reactor that operated safely for decades before being shut down for economic reasons in 2019. The poetic irony of 3 Mile Island, the very name that symbolized nuclear fear in America, potentially being restarted to power artificial intelligence. That's almost too perfect. It captures something real about how the conversation around nuclear energy has shifted. And here's something worth thinking about as you drift off. The total number of deaths directly attributable to nuclear power plant accidents in the entire history of the technology, across nearly 70 years of commercial operation, is surprisingly small. The World Health Organization and the United Nations Scientific Committee on the Effects of Atomic Radiation have extensively studied Chernobyl, Fukushima, and every other nuclear incident. The directly attributed death toll from Chernobyl is in the dozens to low hundreds from acute radiation exposure and thyroid cancer caused by radioactive iodine. The estimated total excess cancer deaths over the lifetime of the exposed population range from a few thousand to perhaps tens of thousands, depending on the study and the methodology. Fukushima's direct radiation death toll is essentially 1. 3 Mile Island, 0. Compare this to other energy sources. Coal power plants, through air pollution alone, are estimated to cause hundreds of thousands of premature deaths every year worldwide. The air pollution from burning fossil fuels, particulate matter, sulfur dioxide, nitrogen oxides, kills millions of people every decade. Hydroelectric dams have failed catastrophically, with the Banqiao Dam disaster in China in 1975 killing an estimated 170,000 people. Even rooftop solar installations cause more deaths per unit of energy generated than nuclear power, simply from workers falling off roofs during installation. This isn't to minimize the genuine risks and tragedies of nuclear accidents. It's to put them in context. Every energy source has costs, including human costs, and by the metric of deaths per unit of energy generated, nuclear power is, statistically, one of the safest energy sources ever developed. The International Energy Agency and multiple independent analyses have confirmed this. The fear of nuclear energy, while understandable, radiation is invisible, its effects are delayed, and the worst-case scenarios are genuinely terrifying, is disproportionate to the actual risk when compared to the alternatives we accept without much thought every day. And maybe that's one of the central paradoxes of nuclear power. It's a technology that we fear precisely because of its power, and that we need precisely because of its power. It's a technology born in war, stained by the memory of Hiroshima and Nagasaki, scarred by Chernobyl and Fukushima, burdened by the unsolved problem of long-term radioactive waste storage. Tens of thousands of tons of spent nuclear fuel sitting in cooling pools and dry casks at reactor sites around the world, waiting for permanent geological repositories that, in most countries, haven't been built yet. Finland is leading the way with its Onkalo repository, a deep geological storage facility carved into bedrock on the island of Olkiluoto, designed to safely contain spent fuel for 100,000 years. 100,000 years. Think about what that means. 100,000 years ago, modern humans were just beginning to leave Africa. The engineers who designed Onkalo had to think about safety on a timescale that dwarfs all of recorded human history. They had to ask questions like, how do you warn people about buried radioactive waste in a language they'll understand 100,000 years from now, when every language currently spoken on Earth will almost certainly be extinct? It's a profound problem, and the fact that Finland is actually building a solution, imperfect perhaps, but real, is quietly remarkable. The waste question is genuinely challenging, and it's important to be honest about that rather than wave it away. Spent nuclear fuel contains a mixture of radioactive isotopes, some of which remain hazardous for hundreds of thousands of years. When you pull a fuel assembly out of a reactor after several years of use, it's so intensely radioactive that standing next to it unshielded would deliver a lethal dose within seconds. The spent fuel is first stored in cooling pools at the reactor site, submerged in water that both cools the residual decay heat and provides radiation shielding. After several years in the pool, the fuel cools enough to be transferred to dry cask storage, massive steel and concrete containers that provide shielding and cooling through passive air circulation. Most of the world's spent nuclear fuel is currently in one of these two forms of interim storage. It's technically secure, but it's not a permanent solution. The scientific consensus is that deep geological disposal, burying the waste hundreds of meters below the surface in stable geological formations, is the safest long-term approach. The basic idea is straightforward. Find rock that has been geologically stable for hundreds of millions of years. Drill into it, and place the waste in engineered containers surrounded by bentonite clay barriers, seal the tunnels, and let the geology do the work. The radiation will decay. The containers will last thousands of years. The clay will absorb any radionuclides that eventually leak out, and the surrounding rock, which has been sitting there since before the dinosaurs, will keep everything contained until the hazard has diminished to background levels. Sweden is also building a geological repository at Forsmark, using a different approach than Finland's. They plan to seal spent fuel in copper canisters surrounded by bentonite clay in granite bedrock about 500 meters down. The United States proposed Yucca Mountain in Nevada as its repository, but the project has been politically stalled for decades, making it one of the most expensive holes in the ground ever, not used for its intended purpose. So here you are, lying in the dark, and the story of nuclear power stretches out behind you like a long, complicated river. It starts with Becquerel's desk drawer and Marie Curie's glowing vial. It flows through Rutherford's atom and Fermi's pile, through the deserts of New Mexico and the cities of Japan. It passes through decades of hope and fear, through grand promises and terrible failures, through the quiet hum of 400 reactors, generating about 10% of the world's electricity, right now, tonight, as you listen to this. The atoms that make up your body contain the same nuclear binding energy that powers those reactors. The forces holding your nuclei together are the same forces that Fermi's pile unleashed in that squash court in 1942. The protons in your cells are held in place by the strong nuclear force, the same force that, when disturbed, releases the energy that can power a city or destroy one. You are, in a very real sense, a nuclear-powered being. The food you ate today got its energy from the sun, and the sun is a giant fusion reactor, fusing 600 million tons of hydrogen into helium every second, converting about 4 million tons of matter into pure energy via Einstein's E equals mc squared. That energy traveled 93 million miles through space, was absorbed by plants, eaten by you, and is now powering the neurons that are processing these words. The nuclear story isn't something that happened over there to other people. It's happening inside you, right now, at the atomic level, and the future of nuclear power is genuinely uncertain, which is actually the most honest thing you can say about it. Maybe small modular reactors will solve the cost problem, and nuclear will experience a renaissance. Maybe fusion will finally work and transform the energy landscape entirely. Maybe renewables and storage will advance so rapidly that nuclear becomes unnecessary. Maybe some combination of all of these will happen. The engineers and physicists working on these problems right now, the people designing next-generation reactors, the plasma physicists chasing fusion, the materials scientists developing fuels that can withstand extreme conditions. They're working on one of the most important engineering challenges of the 21st century. How do you power a civilization of 8 billion people without destroying the planet you live on? Nuclear energy is part of that answer. How large a part remains to be seen. But whatever happens, the story we've walked through tonight is one of the great stories of human ingenuity and human folly, of brilliant science and terrible consequence, of the deepest questions about risk and responsibility and the kind of world we want to live in. It started with a curious physicist leaving a rock on a photographic plate in a dark drawer. It led to the most powerful technology ever developed, and to moral questions that may never be fully resolved. And it continues, right now, in laboratories and construction sites and legislative chambers and public debates, as human beings try to figure out how to live with the power they've unleashed. So let that settle over you. Let the reactors hum. Let the atoms do what they've been doing for 14 billion years, holding themselves together with forces that dwarf anything in our everyday experience, quietly containing energies that we've only just begun to understand and harness. The universe runs on nuclear energy. The stars are nuclear furnaces. The ground beneath you is warmed by the radioactive decay of uranium and thorium deep in the Earth's mantle. You are bathed in nuclear processes every moment of your life, and you always have been. What changed in the last century or so is that we noticed. We figured out what was happening, and we tried to put it to use. The results have been magnificent and terrible, often at the same time. That's the human story. That's what we do. We reach for the fire, and sometimes we get burned, and sometimes we light the way. And right now, tonight, in this moment, the fire is burning quietly in 400 reactors around the world, splitting atoms, boiling water, generating electricity, and doing it without producing a gram of carbon dioxide that would warm the atmosphere. That matters. Whatever you think about nuclear power, whether you see it as humanity's greatest engineering achievement or its most dangerous gamble, that fact matters. So rest now. Let the ideas drift. Let the names and dates and numbers fade into the comfortable blur of half-sleep. The atoms in your pillow are stable. The forces that bind them will hold through the night. And somewhere, right now, a neutron is hitting a uranium-235 nucleus and splitting it in two, releasing energy that will flow through wires and into someone's lamp, someone's hospital, someone's home. The chain reaction continues, and you can let it carry you, gently, quietly, into sleep.